In section 9.7, we're going to look at Taylor polynomials. Now, in terms of Taylor polynomials, this is kind of a different type of section than what we've been dealing with. What we've been dealing with is convergence and divergence of various series. And what we're going to be dealing with in Taylor polynomials is basically these polynomials that approximate other types of functions. So that's really what Taylor polynomials is all about. However, they are going to converge, pardon the pun, in terms of what we were doing earlier once we get into the later sections here, 9.8, 9.9, and 9.10. So what do Taylor polynomials do? They approximate really, really well. So the goal of this section is going to build a polynomial to approximate a function. And when we do that, we're going to approximate the function around a specific location, all right, on the graph. So what we're going to do is we're going to choose a number C. And the phrase that we're going to use is centered at C. So C is the center. That's where our approximation and our actual function are going to match up perfectly. And then the approximation polynomial will approximate that function really, really well close to C. So when it's centered at C, things that are close to C, the polynomial and the function will be really, really close in terms of their output values, close to C. And how we make it really close, how we approximate it really well, is we make the derivatives correct at C. Okay, so we make the derivatives of the polynomial match up with the derivatives of the function around C. So that's what we do. We force this centered at C things. That means our polynomial, we'll call our polynomial capital P. When you input C, the output is going to be the same thing as the output of the function when you plug in C into that function. And then you say, well, since we did that for the outputs, since we made the polynomial and the function the same value for x equals C, let's make the first derivative the same value when x is equal to C. And then let's make the second derivative be the same value when x is equal to C. And you could do this so on and so forth until you, however many n's you want. Maybe you make the fifth derivative the same, the third, the fourth, the fifth derivative the same. Eventually, in order to have a polynomial, we're going to have to stop somewhere at some value for n. But we just make all the derivatives be the same thing. So let me do this by an example. So we're going to find a cubic polynomial approximation for f of x equals e to the x centered at c equals 0. All right, cubic polynomial. That means we want a third degree polynomial. And by the way, if we want a third degree polynomial, that means we're going to have the derivatives be the same for the polynomial and the function up to the third derivative. All right, so this is how we always start out. We say we want a cubic polynomial. So we want a polynomial of degree 3. That means I need to take 3 derivatives. Okay, we'll see why that is in just a moment. So f of x equals e to the x. First derivative is e to the x. E to the x is pretty easy to take derivatives of. Second derivative turns out also e to the x, right? Derivative of e to the x is e to the x. So that makes all of these derivatives simply be e to the x, okay? By the way, we want to center this at 0. So what this means is that if you plug in 0 into the function, well, notice that you get 1. If you plugged in 0 again, e to the 0 is 1. Hopefully, I don't need to explain that. Let me move this forward just a bit. There we go. If you were to plug in 0 into the first derivative, e to the 0 is once again 1. Into the second derivative, let's do that. Oops. Plug in 0, you end up with 1. By the way, this is what you should be writing down if you're taking notes. Make sure that you write this down. Third derivative, plug in 0, you end up with 1. So basically, you want your polynomial to be of degree 3, but you want it to, each time when you take a derivative and you plug in 0, you want to end up as a 1. So here's the deal. And by the way, this is the notation. A lot of times people will write polynomial sub 3 to mean the third degree Taylor polynomial. So we need to focus on these coefficients. And what we do is, since we're going to center this at 0, we're going to think of the coefficient, let's call this A3, hopefully x to the third, plus A2x squared plus A1x plus A0. All right. Now, the reason why we're using the polynomial in this way is because we are centered at 0. If I were to have centered at another number, let's say I centered it at 2, it turns out I would have written the polynomial as centered at 2. So instead of having just an x there, I would have wrote x minus 2. All right, I would have shifted the middle or the center of the polynomial over. Obviously, we don't do that here. So this x, think of as just x minus 0. Now that's the polynomial of degree 3. What we know is that when you plug in 0, we want to get out 1. Now let's plug in 0 into this polynomial here. If you plug in 0 into this polynomial, you are going to get 0 to the third power there. You are going to get 0 to the second power there. You are going to get 0 there. Let me scoot this back a little bit. And so when you plug in 0, you should end up with the same thing that you plug in with the function as a 1. So you plug in 0, you should get 1. Now notice what these parts do. A3 times 0 to the third plus a squared times 0 second plus a1 times 0. Basically, what this says is that your P3 of 0 should have an A0 value of 1. So P3 of 0 should be 1. That forces A0 to be 1. All right? And we're going to keep doing that. Now, let's take the derivative. First derivative needs to match up, first derivative of the function when I plug into 0 needs to match up the first derivative of this polynomial when I plug in 0. So let's take this polynomial and let's take the first derivative of that polynomial. So the first derivative of this polynomial is going to be 3 times a to the third x squared. I said a to the third, a sub 3 x squared plus 2 a2 x to the first power plus a1 times x to the 0 power. And then the a0 is going to go away. So again, 3 goes out front, 2 goes out front, 1 goes out front, lower the exponents by 1. This a0 goes away. Now that's fine because what we are trying to do is we're trying to match up what's going to happen when you plug in 0. So if I want my function, when I plug in 0 into my first derivative, if I want the first derivatives to match up, what that means is when you plug in 0 in for x into the first derivative of the polynomial, you should end up with the number 1. Oops. And notice what this is forcing. This is forcing, again, the terms with the x's are going away. This is forcing this a1 to also be 1. All right? So when you plugged in, I messed this up a little bit. When you plugged in 0 into your original function, that forced your constant to be 1. Now your coefficient of x on your original polynomial is also forced to be 1. All right? Now you can imagine what we're going to do here beyond that. Let's take the second derivative. You're going to get 3 times 2. So you're going to get 6 out in front, x to the first. You're going to get 2a2, and then so when you take the derivative of 2a2 x to the first power, you just get 2a2. Derivative of a1 goes away. Plug in 0 like we did here, or like we've done before, I should say. So plug in 0. When you plug in 0, it needs to match your function. Your function value when you plug in 0 is 1. Therefore, second derivative has to be 1 when you plug in 0. And we get 2a2 has to be 1. Now, notice that this does not give you the a2 has to be 1. In fact, this tells you that a sub 2 has to be a half. All right? So be careful about that. Now, the last step is the third derivative. Third derivative is, well, when you take the third derivative, you get 6a3. 6a3, whoops, excuse me. 6a3. Plug in 0. Oops, that's a weird symbol there. You need to get 1, so you get 1 is equal to the, oh boy, polynomial of degree 3. Plug in 0. You're getting 6 times a3. Now again, notice that what we have here is not that a3 has to be 1, but rather 6 times a3 has to be 1. So a3 has to be 1/6. And what that means is that if I look up at my original polynomial, now I have a way to find a sub 0, I have a way to find a sub 1, I have a way to find a sub 2, and I have a way to find a sub 3. So that original polynomial is forced to be 1/6 times x to the third plus 1/2 times x squared plus 1x plus 1. And so e to the x, my original function, can be approximated by that polynomial of degree 3. And that is called a Taylor polynomial. All right. And again, sometimes we say at center of 0, or can be approximated by the following Taylor polynomial of degree 3 at centered at 0. Sometimes people say that way too. Natural question to ask from right here. Well, there's a couple of natural questions to ask. First is, how good of an approximation is this really? So let's take a look at a graphing calculator. Now I've already graphed, hopefully you can see that, f of x equals e to the x. That's the red line here. And what we're trying to do is we're trying to get a polynomial that approximate this graph well, right around this area where x is 0, okay? So let's type in my polynomial, 1/6 x to the third plus 1/2 x squared plus 1x plus 1. So notice what that blue polynomial does. Right where x is 0, this blue polynomial really mimics the graph of e to the x really well. Now, obviously, when we start getting further away, when you get out to x equals -3, then it's a really bad approximation. When we get up to, x equals 2 or x equals 3, then we get a bad approximation. But this is a really good approximation polynomial around where x is equal to 0. So that's really what these polynomials do. They approximate well. This polynomial approximates this function well right around where x is equal to 0, centered at c equals 0. Now you might ask, well, that was all fine and dandy for centering things at 0. What happens if we want to center this at a different number? Let's say we wanted to, instead of centering e to the x at 0, what if we wanted to take and find a cubic polynomial approximation for this function centered at c equals 2? So we'd go through the same process. Now, some of this is already done for me, so that's really, really nice. If I start out by saying, well, my function is e to the x, the first derivative is still e to the x, second derivative is e to the x, third derivative is e to the x. By the way, obviously e to the x is one of the nicest functions to take derivatives of, but that's fine. If you plug in 2, well, you just get e squared. Nothing really fancy there. You're not getting 1 anymore, but you do get e squared every time when you want to center it at 2. And the other thing, centering this at 2, this was a third degree polynomial. I forgot to tell you that. So we want to make sure that we have up to third derivatives when we do this. The other thing is, when you go and you try to find coefficients, you could write your polynomial like this, but it turns out your polynomial is much easier to write or to deal with if we want to center it at 2. Instead of writing x, write x minus 2 instead of x for every time you deal with an x. So instead of x, x minus 2. Instead of an x, x minus 2. I think I'm running out of room, so I might copy that and paste it at a slightly different spot. By the way, it's pretty clear the obvious advantage of this is that when you plug in 2 into this polynomial, this piece here goes to 0, this piece here goes to 0, this piece here goes to 0. Whoops, I forgot take that off. And the only thing you have left is a sub 0. So if you plug in 2, a sub 0 has to be e squared. Okay? Also, these aren't bad to take derivatives of. If you take a derivative of this polynomial degree 3 centered at 2, what you end up with, the 3 comes out front, 3 times a 3, and then the, x minus 2 is going to be raised to the second power. Now, normally you have to multiply times the derivative of the inside function, but the derivative of the inside function is 1, so I don't need to multiply by anything. So you'll notice that the pattern here is every time you replace an x with an x minus 2, everything else kind of stays the same. So you get that as your first derivative. And this means that when you plug in 2, e squared, thought I hit that right. E squared is what you should get when you plug in 2. When you plug in 2 to your first derivative, this shows that a1 has to be e squared. You can do the very, very similar thing with the second derivative. Second derivative, 2 comes out front, 3, a to the 3, x minus 2 to the first power. You get 2a2, and then the a1 goes away when you take a derivative. So what this is saying is that e squared, since that has to be what you get when you plug in 2 into your second derivative, has to be 2a2. So notice that what's happening here, 2a2 is e squared. That means e squared divided by 2 is a2. And in a similar way, third derivative is 6a3. That means e squared has to be equal to what you get when you plug in 2 into the polynomial, which is 6a3. Now, what that means about this polynomial of degree 3, well, the Taylor polynomial is going to be this polynomial. X minus 2 is going to get raised to the third power. X minus 2 is going to get raised to the second power. X going to get x minus 2 to the first power, and so on and so forth. And everywhere we had an a3 before, we had an a0, we can replace that with an e squared. a1, you can replace that with an e squared. a2, you can replace that with an e squared. So over 2. a3, you can replace with an e squared over 6. So everywhere we had a 1 in this spot, that could be replaced with an e squared. Here, e squared over 2, e squared, and then e squared. Whew. That's a long process, but you can see that this is going to approximate f of x equals e to the x really closely, centered at 2. And we can take a look at the graph if we'd like. So what do we got here? E squared. Oh. E squared. E squared. E. So hopefully they did not graph that very well. Times. That is not the graph of what I'm looking at here. I think they're giving me another variable. So let me try to fix this real quick. All right, there you go. Now I wrote this correctly. Polynomial I dealt with, e squared over 6 times x minus 2 to the third plus e squared over 2 times x minus 2 to the second plus e squared times x minus 2 plus e squared. And you'll notice at the value of 0, these things don't match up very well anymore. But at the value of 2, which is right there, roughly, this does match up pretty well, okay? So at the value of 2, the blue and the red lines match up really, really well. In fact, they match up for quite a ways on either side, all right? So red around 2 is very close to the blue around 2, all right? So that's what Taylor polynomials are accomplishing. Now, obviously, there's a pattern here. Hopefully, you saw it. And basically, the nth degree Taylor polynomial centered at C for f of x, that's an approximation for f of x. The coefficients, well, let me start with this. You're going to start with x minus c to the nth, x minus c to the nth minus 1, all the way down to get x minus c to the first, and then no x minus c. And it turns out those coefficients are just the derivative when you plug in c divided by 2 factorial divided by 3 factorial divided by n factorial. So if we were looking at our third degree, the reason why we were always dividing by 6 was because 6 is 3 factorial. 2 factorial is 2. That's why we were dividing by 2 with the second degree term. I don't write over 1 factorial, but you could write over 1 factorial here for the first derivative. And if you want to write over 0 factorial, you could here. So basically, what we're saying is that the following. We're saying that for a Taylor polynomial, the nth degree term is always the nth derivative, plug in c, divide that by n factorial, and then multiply by x minus c to the nth power. So if you take the sum of that from 0 to whatever value of n we're looking at, that's going to be the Taylor polynomial. And again, you can see why we happen to always need this n factorial, because when we take these derivatives, let me go up to the very first example we did. You know, the first derivative, that 3 is going to come down front, then the 2 is going to come down front. You could imagine if we started with an x to the 5th, the 5 would have come down front, then the 4 on the next derivative, then the 3 on the next derivative, then the 2, then the 1. So that's what's going on with these Taylor polynomials, okay? Every term is nth derivative, plug in c, divided by n factorial as your coefficient, and your coefficient is of x minus c to the nth power. Now, it happens that a lot of times these things a lot are centered at 0. 0 is a very popular centering spot. And when that is the case, then we have a special name for that. That's called the Maclaurin polynomial. So the Maclaurin polynomial is what the Taylor polynomial is when c is 0. Okay, so if you ever see that terminology, Maclaurin polynomial, that just means Taylor polynomial centered at 0.